Right, happy Monday. So last week we talked generally about sequences and series. What we're going to do, and I think it actually makes it a little bit easier, is we are going to look at, we've seen these already, but we're going to look at two specific types and patterns. The first today that we're going to see is called an arithmetic sequence, and then thus an arithmetic series. So there's two types, arithmetic and geometric. We're going to start the next 2 days with arithmetic sequences, and we'll move on to geometric. So an arithmetic sequence is a special type of sequence in which, as we go from one term to another, it has a common difference between the consecutive terms. This means that you are adding or subtracting the same number each time. So it would be +4 to get from each number to the next, or -5 to get from each number to the next. So the nice thing about this is that if the sequence is arithmetic, there is a explicit rule that gives us a formula that we can follow. So for an arithmetic sequence, if I just want to plug in any specific number for n, the explicit formula is this. The nth term, so a sub n, is going to be a1 plus d times n minus 1, where we're going to make the note that d is the common difference between our terms. So d is our common difference, whatever number we're adding or subtracting. So we can think about this, and we could go back and we could kind of break down where this pattern comes from to make it make a little bit more sense. But this formula here will always work for an arithmetic sequence. Just like we're able to write things explicitly, we can also write them recursively. And so for our recursive formula, the first thing is that we always need to know with a recursive formula what the first term is. So whatever a1 is, we would state that. And then for the nth term, since we are just adding or subtracting the same number, then for the recursive formula, we want to take the term right before it, an minus 1, and then add our common difference onto it. And that number could be positive or negative. So this is one way to first start and break down different formulas and look at the different types. So, or different sequences and use the formulas. So here with example 1, we are given two arithmetic sequences. The first thing we can see is, why are they an arithmetic sequence? Well, as I look, how do I get from 7 to 16? There's not a clear multiplied number, but I do go and I add 9. And then we want to verify it's the same thing. To get from 16 to 25, we're adding 9. And same again here. So it looks like it is the common difference. It's not changing. I'm adding 9 every single time to get to the next term. So for the explicit rule, it's the first term. So our nth term is equal to the first term. So in this case, that's 7. So it's 7 plus. And then the common difference is this number that we're adding every time. So that makes d 9. So this is plus 9 times n minus 1. Now this next step is optional. Some people will distribute the 9. And so they would make this 7 plus 9n minus 9, and then they would add this together to make this 9n minus 2. Either way works, whichever formula you prefer. One just combines it a little bit more simple, but it still is an explicit formula where I could plug in. So now we'll do this in a second. I could plug in a number and I could figure out exactly what term I'm on. For the recursive formula, remember that the recursive is always defined by the term right before it. So we always need to see what the first term was. So a1 was 7. And then for the an term, our formula tells us we take the term right before, which we write as an minus 1, and then we add our common difference. We take the term before and we add 9. So to get from 7 to a2, we take a1, which is 7, we add 9, that gets us to 16. So that's example number 1. If you feel like you understand it, want to try it, pause here, do 1b, and then play it and see if you get the same thing. But now we're going to do 1b. So again, looking between these numbers, I don't quite see a clear number that's dividing to get between them, but we are subtracting 3 every time that the numbers go down. They're going down by 3. So that is our common difference. So d is -3 and our first term, a1, is 4. So when we go to make an explicit sequence, remember, as you get familiar with it, go back and reference the formula. It takes time to learn it, but use this formula, memorize this formula. So our nth term, an, is equal to the first term. We're always going to fill that in with a number. So we know that that's 4 plus, and then our common difference of -3, and then times n minus 1. Think of n like our x. We want to leave n in the formula every time. And then just like we did before, if we want to, we can distribute this, which would make it 4 minus 3n plus 3. So that would make this 7 minus 3n. Either way, this formula is an explicit formula to continue our sequence. And then lastly, for the recursive formula, we need the first term, so a1 is 4. And then the nth term, always defined as the one before it. How are we getting from one term to the other? We're taking the term right before it, which we say with as an minus 1, and each time we're subtracting 3. So this here is our recursive formula. So now moving on to number 2, they ask us to find the 124th term of the sequences above. So you could say it's pretty easy to just add 9. If I asked you to find the 10th term, I already know the first 5. It's not that much work to keep adding on 9, but if I were to keep adding on 9 124 times, that is going to be a lot of work and something we don't want to do, and that is where these explicit formulas come in to be helpful. So the reason explicit formulas are helpful is if I want to know the 124th term, that's a 124. And I can go up and I can use my formula to figure that out. So you could either use the simplified or the non-simplified. I go back and forth. So let's say that we use the simplified formula. This is 9 times n, which is 124, and then minus 2. So what that gives us here is if we do 9 times 124, that's 1,116, subtract 2, and that gives us an answer of 1,114. It would take a lot of adding to get up to that number. So that's our answer for A. Then for B, just so I'll show you, I'll use the non-simplified formula. So if I wanted to find the 124th term of that sequence, if I use the non-simplified, you could use either. It's -4, and then I'll just write that as a -3, times n minus 1. That's 124 minus 1, so that's just 123. So now I need to do 4 minus 3 times 123. And when we work this through, that gives us -365. So this is a way to show you first how to write an arithmetic sequence with an explicit or recursive formula, and then how to use the formulas we made to find later terms. We'll do a lot of this here in a second. All right, next up is something a little bit more complicated. So I'm going to shrink these here so that we can see it. All right, number 3. Find the first 5 terms of an arithmetic sequence given that the 8th term, A8, is 26, and the 12th term, A sub 12, is 42. So if we think about this, we know it's got 1, 2, 3, 4, 5, 6, 7, 8. This term has a value of 26. 1, 2, 3, 8, 9, 10, 11, 12. So that means this term is 42. Well, there's some common difference that's getting me from 26 to 42 and then all the way back to these other numbers, but we have no clue what that is. So this plus something, and then we also have a number that we started on, and we have no clue where we started. So to find the first 5 terms, I have to know that. This is where our formula comes into play. For the 8th term, remember that the formula is A sub n is equal to A1 plus D times n minus 1. Currently, I do not know what A1 is, nor do I know what the difference is. But let's see what we can do with that. So if I said, okay, when I'm at the 8th term, that means n is 8. That gives us the formula that A8 is equal to A1 plus D times 8 minus 1. Now, I know here that A8 is 26, so that means 26 is equal to A1. And then 8 minus 1 is 7, so we can write this as plus 7D. So that gives us some equation to work with. Now I want you to start thinking of a system. I have two variables, two things I don't know, so I need two equations. Well, that is exactly where this next piece of information, that the 12th term is 42. So when n is equal to 12, this means that A12, which is 42, is equal to A1 plus n minus 1 times d, which is 41d. If you got confused with the 41d, go back to the formula. Look how we did n minus 1, and I just wrote that number in front of the variable. So now we have to solve this out. And so at this point, because we have two variables, we can use a system of equations to solve this out. And I don't know why, I'm so sorry here, I just wrote the wrong thing. If you were confused why I got 41, I was looking at the answer. It is n minus 1, so and n is 12. So that should be 12 minus 1, which would make this 42 as A1 plus 11D. Thank you for sticking with me here. Okay, all right, that's a little bit better. 11D, that's what we want. Okay, so going back to this, we have a system of equations. Remember with systems, back to algebra, there's two methods. We could use substitution or elimination. I'm going to use substitution. So I'm going to take this equation here and solve it for A1. So A1 is equal to 26 minus 7D. So then now we're going to go over to the A1 in my other equation, and we're going to make a substitution. So that makes this 42 is equal to 26 minus 7D plus 11. So now as we go to solve this, the parentheses around it, there's nothing in front, so we can remove them. We subtract 26. That gives us that 16 is equal to, and then negative 7 plus 11, that's 4D. And if we divide by 4, that gives us that our common difference is 4. So we at least now know that to get from each term to the next, we are going to add 4. But the last problem is we need to know where to start. If we go back over here, the first term was 26 minus 7 times D. Now we know what D is, so that means that A1 is 26 minus 7 times 4. That's 26 minus 28. That's a value of negative 2. So then now, if we work off to the side, they ask us to find the first 5 terms. So the first term is negative 2. We're good there. So then to get to each term, we're going to add 4. So that makes A2, 2. That makes term A3 add 4, 6. And then term A4 is going to be 10. And term A5 is going to be 14. And now we have found our first 4 terms. And that is, or our first 5 terms, and that is the end of this problem. The big idea with this one that shows us how we use a system of equations to solve this through. All right, so that is sequences. We can write them as explosive and recursive sequences, and we have these two main formula here, and then we can use those. Now we're going to take it a step further and turn these into an arithmetic series. So I'm going to shrink this. The big thing to remember about a series is that a series is a sum of a sequence. So what people have found is that for an arithmetic sequence, we can pick a certain number of terms, n terms, that we want to add up, and they have found a formula that gives us the pattern for what these terms add up to, and here it is. So for the sum of the first n terms, remember we call this a partial sum, Sn, it is equal to n over 2, the number of terms that we're adding, times a1 plus an. So it's the first term plus the last term times n over 2. So if we're adding up the first 50 terms, it's 50 over 2. The first term of that series of 50, and then the last term of that sequence of 50. One last thing to note here, we're not going to go too much into this, but if you make the substitution for the formula, explicit formula here, you can also work down to this formula. I personally prefer the one I gave you, but it's up to you. So now we're going to use this to find the 10th partial sum of the sequence. So what I know is I need to know, in this case, A1, but I also need to know A10. I currently know that A1 is 8, but I don't know, I know the first 4 terms, but I don't know the 10th. This is where our explicit formula comes into play here. What is my common difference? How do I get from 8 to 26? Well, if I find that common difference, that is a common difference of adding 18, and then same again to get from 26 to 44. So I could, for A10, use the formula that it's the first term, A1, which is 8, plus my common difference of 18 times n minus 1, which is 9. And then when I solve this through, that gives me 18 times 9, which is 162, plus 8, which is 170. So now when I go to my formula, the 10th partial sum, S10, is equal to, and if we look back up, so it's n over 2. N is this little subscript here, so it's 10 over 2. We're adding up 10 terms, and then times the first term, which is 8, plus the last term, which is 170. That gives us 5 times 178, and that comes out to 890 for our partial sum. So our partial sum here comes out to be 890, and we used our arithmetic sequence formula to find one of our terms. So let's do another one. This time they gave it in our sigma notation, but it's still the same thing. Find the partial sum of from term 1 to term 84, and then they actually gave us the formula. It's 3k minus 7, and because these values there's a multiplier and it's starting going up from -7, we can see here that this is going to be an arithmetic sequence. So for our partial sum, we need to know the first term, and then in this case, we need to know the 84th term. So for the first term, since they already defined the explicit sequence for us, we just need to plug in 1 for k. So that's 3 times 1 minus 7, which gives us a value of -4. And then for a sub 84, that's 3 times 84 minus 7, which comes out to 245. So now for our partial sum, it's the 84th, we're summing up 84 terms, so n is 84. So in this case, this is 84 over 2, and then times the first term, a1, which is -4, plus the last term, which is 245. This gives us 84 divided by 2 is 42 times 241, and this gives us a partial sum of 10,122, which would have been a lot to find those 84 terms by hand, so we should be really thankful that we have this formula. Otherwise, we would have had to just write them all out and add them up, which is possible, it just would have taken a lot of time. So before we finish here, I know this is a longer video, but this last example is very important. I want you to look, before I tell you, what is different about this sigma notation partial sum versus the one that we had above. Well, hopefully what I want you to notice is that there is an n equals 20 at the bottom. Normally it starts at n equals 1. So they want us to add up the terms from the 20th to the 34th. We can use our formula still, we're just going to have to make a couple of adjustments. So in this case, you want to think of n not as just that bottom number, but as how many terms we're adding up. From 20 to 34, how many numbers is it that we're adding up? So if you think about from 4 to 10, how many numbers you're adding? 4, 5, 6, 7, 8, 9, 10. If you count that on your fingers, 10 minus 4 is 6. You'd think you're counting up 6 numbers, but there were 7 numbers counted. I used my fingers to count this. So it's always going to be a little bit more. So in this case, for our formula, how many terms are there between 20 and 34? The general way to figure this out is that our n in this formula will be the upper bound minus the lower bound plus 1. So for our problem, n, the number of terms that we are taking a sum of, is 34. Oops, hold on here. 34 minus 20. plus 1, and that gives us a value of 15. That means that we are adding up 15 terms between 20 and 34. So now going back, I do still need to figure out what those terms are. So in this case, my A1 is happening for our explicit formula when n is 20. So that's negative 2 times 20 plus 3. When we work that through, that gives us a value of negative 37. And then for the 15th term, that's going to happen with my upper bound of 34. So we are still using the value 34. We want to be at that point in the sequence. We're just using n to represent the number of terms that we're adding up. We're only adding up 15 numbers. So that's negative 2 times 34 plus 3. That gives us a value of negative 65. And so then lastly, we have everything that we need. It's just going to look a little bit different. So the partial sum of S15 of 15 terms of this sequence will be n, which is 15 over 2, we're adding up 15 terms, times the first term in the sum, which was negative 37, that happened at n equals 20, and then plus negative 65, or I'm just going to write as minus 65. 15 divided by 2 is a fraction, or 7.5, and then negative 37 minus 65 is negative 102. Multiply those together, and that gives us a partial sum of negative 765. And that is the end for our notes here. We have seen a sequence given this explicit formula and this recursive formula, and then we also found the rule for a partial sum of an arithmetic series, which is the formula that is given right here. I've added some extra practice, and the notes keys show these examples. If you want to do more practice in addition to the practice that you can, these are not required, and we're not going to work through them in the video, but there are solutions in the answer keys. All right, on to 10.2 day 1 practice set.